Let's continue. And the last one I was talking about, the molecules are really in random motion. They obey in Newton's laws of motion. Now also, I will say they have perfectly elastic collisions, which means energy is conserved. Now also, I will say the pressure of the gas is created because of the collisions with the wall of the container. These are really assumptions that we have assumed so that we will be able to derive an equation for the pressure. And I will not go over the derivation. I will say right away, P equals N M Vx squared. And here just I want to maybe a little bit pause and say that P here, it is the pressure, which is defined as the force per unit area. It is measured in pascals. Now, Vx here, it is the speed of the molecule N, it is the number of molecules. And of course, this is meters per second. Number of molecules, it doesn't have any, I would say, unit. Now, also, we need to know that the velocity can have 3 components. Now this one here, it's along the x-axis, but of course I might have also a velocity along the y, a velocity against along the y, a velocity along the z. And because we will say like it's random motion, then we can assume that all of them, they gonna be like equally. And I will say PV is gonna be 1/3 in M V squared average, and that is gonna be 2/3. And I just because I want to have the kinetic energy, V squared average. And finally, I can say that PV equals 2/3 K translational. K translational, it is the 1/2 mv squared average. Now, as a conclusion, we can say K translational, it has to do with 3/2 N RT. And I will say this here, N, it is number of moles. R, it is the universal gas constant. And T, it is the absolute temperature or the Kelvin temperature. And of course here this has units of joules. Also, what I can do is we can rewrite that expression as having K average as 3/2 kT. Now that K here, K, it is called Boltzmann constant. It equals R/NA. Remember, NA, it is Avogadro's number, and equals 1.381 10 to the negative 23 joules per molecule Kelvin. And I can also, using this equation, I can also reach another way of the equation of state, PV equals NKT. Then these two are really equivalent, these two equations. Now I can also derive here what is called the molecular speeds of an ideal gas. And there is an average value that I'm looking for. We call it RMS, and that is the square root of V squared average, and that equals, of course, 3 kT over M, or 3 RT over uppercase M. Now M here, the lowercase, it is mass of the molecule, and it should be in kilogram. And uppercase M, it is the molar mass, and that one is gonna be kilogram per mole. Okay, just pay attention to these two. And therefore I can say here that although the kinetic energy for two gases, that they are really mixed together, and they are in thermal equilibrium, although the kinetic energies, they're gonna be the same because of that equation, but when it comes to their average velocities, it's gonna be different. Okay, thank you, and I'll see you in a new video. Thank you.